Question 11, let's have a look at what's happening here. Here's the diagram they give us. We're told that this slope is smooth and this slope is rough, and that the two of them are going to accelerate. And if they're going to accelerate, and we're told that the acceleration for both is 1.9 meters per second, so if they're both going to accelerate in that direction, they're both moving. So in other words, the frictional force must be a maximum, and it must be acting to the left on P. Let's have a look at some of the other forces which are acting. There we have R1. I've got another normal contact force there, which I'll call R2. The weight of P obviously is acting vertically downwards. P is 4 kilograms, so that's 4G. The weight of Q is acting vertically downwards. Q is 6 kilograms, so that's 6G. And if I just put some angles in, this one here is 60 degrees. If I put in that line that's in the same direction as R2, this one here is 30 degrees. I'll put some more in later if necessary. We've also got tension acting. The tension is tending to make P move to the right, and the tension is slowing Q down. So the tension acts upwards for Q. So first thing I'm going to do is I'm going to look at P, and I'm going to realise that P is not moving vertically upwards or downwards, so R1 must equal 4G. And we also know that F max is equal to mu R, in this case it's R1, so F max must be 4G mu. So let's have a look at Newton's second law then for P. So I'm going to use Newton's second law for P, and obviously that's going to be to the right because that's the direction that P is accelerating in. So the force is acting on P. To the right we've got the tension. Against that we've got F max, and that must equal the mass of P, well that's 4 multiplied by its acceleration, which we're told is 1.9. So T minus, I know that F max is 4G mu, so 4G mu must equal, and 4 times 1.9 is 7.6. I can't do anything else with that, I'm just going to leave that as number 1. Now let's do Newton's second law now for Q. So that's going to be down the slope because that's the way the acceleration is going. Now if we look at the forces acting on Q, acting down the slope, we've got the component of the weight, which is going to be 6G cos 60 degrees. Acting up the slope, against that we've got T, and that must equal the mass of Q, which is 6, multiplied by its acceleration, which is also 1.9. Now cos 60 and sine 30 are both a half, so in fact it's 6G times a half, so I'm just going to simplify that to 3G minus T equals, and 6 times 1.9 comes out as 11.4. Now from that I can work out T. If I just move T to the right, T then is going to be 3G minus that 11.4, so T comes out as 18 newtons. Fine. If I now want to substitute back in to find mu, I'm going to put that value of T into that one, so I've now got 18 minus 4G mu will equal the 7.6. So 4G mu, if I move that to the right, must equal 18 minus 7.6, which, where are we? So the 4G mu is going to equal 18 minus 7.6, well that's just 10.4. So mu is just 10.4 divided by 4G, and that comes out as 0.2653, so 0.265 to 3 significant figures. Okay, we're now told that 1 second after the whole system is released from rest, so when T is equal to 1, the string actually breaks, and at that point P is actually 0.8 meters from A. So we're going to have a look at what happens to P after that. First of all, though, I'm going to work out the speed that P is travelling at when the string breaks, in other words, after 1 second. So I know that the acceleration of P is 1.9. I know that the time taken for that first bit of motion was 1. I'm looking at the initial velocity, because the system was released from rest, was 0. So I'm trying to find v. So I'm just going to use v equals u plus at. So very simply, u is 0. So in other words, it's just 1 times 1.9. So the final velocity of v when the spring breaks when the string breaks is 1.9 meters per second, and that is when P is 0.8 meters from here. What I'm going to do, I'm just to show what's happening now. This tension is going to now disappear. Let's just remove that. So the tension here now disappears. So let's just get rid of that. So P is now moving along, initially at 1.9 meter per second, but because that has now disappeared the string, it means that that acceleration is now going to change. So I'm going to work out the new acceleration of P. So if we look at the forces acting on P now, the only force acting is F max. Now F max is going to be the same because actually R1 is still equal to 4g, so F max is going to be exactly the same as it was before. And if we look at what F max actually was, oh yeah, sorry, up here we can see that F max is 4g mu, and we know what mu is, so F max is still the same as before. F max is 4g mu, and if I work out F max, and actually I'm going to keep it as 4g mu for now. So Newton's second law then on P to the right, because that's the direction the acceleration is going to take place in. We've got nothing acting to the right, so it's literally just 0 minus the F max, which is slowing it down, is going to equal the mass of P, which is 4, multiplied by its acceleration. So in other words, 0 minus 4g mu is going to equal 4a. And if I carry on, A then is just going to equal minus 4g mu, which is F max, divided by 4. The 4's cancel, so that's minus g mu. I've got my value of mu, which I saved over here in my memory. A then comes out as nice round minus 2.6 meters per second per second. So what we've now got is P moving to the right with an acceleration of minus 2.6 meters per second. So let's have a look. So in that subsequent motion, initially, so we worked out the final velocity of P when the string broke. That's now going to become the initial velocity because we're looking at the second part of the motion. So U is 1.9. We're told to look at the distance when P comes to rest, so V will be 0. A is going to be minus 2.6, and we want to find the displacement. So I'm going to use V squared is equal to U squared plus 2AS. So 0 is going to equal 1.9 squared plus 2 times that minus 2.6 multiplied by S. So if I keep going over here, if I move that to the other side, that's actually minus 5.2. So if I move it to the left-hand side, it becomes 5.2S is equal to 1.9 squared. So S is going to be 1.9 squared divided by 5.2, and that comes out as 0.694. Now, what happened is that we were told that the string broke when P was 0.8 meters. So here's where P was. This is A. When P was 0.8 meters from A. The string broke and the displacement is 0.694 meters. So we're told now to work out how far P is now from A. So I'm going to have to do 0.8 minus the 0.694. So that distance comes, so basically 0.8 minus 0.694. That's the actual distance from A. That comes out as 0.106 meters or 10.6 centimeters.